possibility of architectural flaws. I've made a distinction between architectural flaws and bugs in the code because kernel code is, as I said, is designed to provide services to user mode. And it may be a situation where a service is provided that is actually doing what it's supposed to do, but what it's supposed to do breaks operating system security levels. So a device driver, for example, in a rootkit disinfection system that can copy chunks of memory around from arbitrary areas, could be leveraged, obviously, to overwrite structures in the kernel and allow arbitrary code execution in the kernel. Bugs in the code, these are standard things, though there are issues with exploiting them. There is internally what could be thought of as a heap, paged pool and non-paged pool, that due to the way the kernel works, that those are extremely instance specifics for exploiting. There's no way you can do something like heap feng shui, because if you just sprayed the kernel heap, you would have a blue screen pretty much instantaneously. Subverting operating system initialization. EI's boot root and the vbootkit have already been talked about publicly. The vbootkit talk, I think, has been pulled from BlackHat over here, unfortunately. But if you're interested in that kind of thing, then you can refer to that research. Something else not normally talked about is actually modifying the kernel modules on disk. You need to have some privilege level to do this anyway, but I used to work in antivirus, and I've never seen a kernel module infecting virus, though there is no reason why they can't be. And kernel modules also support DLLs, so to speak, export drivers, which will be loaded up as part of their initialization. So the tools I use for assessing kernel code, I'd like to break them into two different areas depending on what I'm doing: static and dynamic analysis. Dynamic analysis, by that I mean runtime analysis, so tools that monitor what's going on, that can actually probe a driver in the kernel at runtime. And static analysis, disassembler, or source code auditor. Dynamic analysis can never guarantee results. And because if you do hit a bug in kernel code, it will cause a blue screen. Fuzzing can be awkward to automate. I'll mention some ways that you can later on, though it still is awkward. Static analysis allows you to cover every potential path of execution if you want to, but that's obviously time-consuming, and if you only have a binary, as I sometimes do, then that can be quite complicated as well. Microsoft provide several tools for kernel developers to help them assess their own code, and some of these tools will be used when the device driver is submitted for certification by Microsoft. So it will have a certificate particularly useful for Vista, which has a mandatory code signing policy. They have the SDV, the static driver verifier, which requires source code and will check for typical bugs in the code, so null pointer dereferences, race conditions, and things like that. Prefast, which is fairly similar. Disassembler, I typically use IDA because it's pretty much the best disassembler out there. And the Windows driver kit, mainly for the information it contains that's more difficult to get hold of, particularly the header files that provide you documentation on the structures in the kernel and things like that. Dynamic analysis. I do occasionally have discussions with people about which debugger to use. It's obviously a question of personal choice. I use WinDebug almost exclusively nowadays. It is, as far as I'm concerned, the only suitable kernel debugger for Windows. Granted, you have to run it in a remote setup with one computer debugging another computer, or a VMware, virtual machine VMware or virtual PC, which can be more awkward, but that has the added bonus of having greater stability for the operating system because you're not running the debugger on the same machine. Plus, the integration it has with Windows makes life an awful lot easier. The driver verifier is an internal component of the Windows kernel. It can be enabled to verify random drivers or specific drivers, and will do things like emulate low memory conditions or randomly fail APIs. There are other various tools I use to extract information, such as WinOb from sysinternals, which allows you to browse the kernel's object directory, so you can check ACLs or and things like that. NT dispatch points. Access will go and read device driver's dispatch table. So if it supports the IO control interface, you can find where those entry points are in the kernel, and then either fuzz them or analyze them statically. And rootkit hook analyzer from resplendence.com. This is an interesting tool. Not only does it find hooks in the kernel, it also allows you to fuzz them if you want. It comes with the obvious disclaimer: if you fuzz this and it finds a bug, then it's going to crash. So that can be quite useful if you're going to do some fuzzing analysis on hooked system calls. The only other issue with that is it only fuzzes system calls, so it's not going to fuzz any other hooks that are potentially there. I'll come into other possible hooks later on for when talking about PatchGuard briefly. So I've gone over the tools and the architecture. We're looking for poor access control, so functions that should not be functions or structures such as shared memory sections that should not be accessible by unprivileged users. This can typically be mitigated by checking for specific privileges in the kernel, because when a thread transitions to kernel, does a system call or whatever and transitions to kernel mode, it's still running as the same process. So you can put access control such as a debug privilege if you want, or TCP privilege, a trusted computing block, I think, and just check for that. Trusting user-supplied data, I already mentioned this, pointers and lengths, this is a typical issue. As I said, any buffer that's passed in that does not that has pointers or structures contained within it that have lengths, that has to be verified by the device driver itself. Microsoft, for the updated documentation for the Vista display architecture, specifically say there are several APIs that you have to validate the data that's coming in for if you're going to use it in as a length or as a pointer. There are typical coding bugs that you'd expect for user mode code, such as boundary conditions or off-by-one errors or signness issues. These are typically more difficult to exploit, as I said, if you if you overflow the paged pull or non-paged pull in the kernel, then you've got very little idea of where that is or what you're overwriting, so likelihood is it's going to go down immediately. Of course, if this is accessible over a network, then that's still pretty good. If you can, say, have a UDP broadcast packet and just take down a whole bunch of machines, that's pretty serious. And as I mentioned earlier, design flaws, so exposing kernel functionality or data to user mode, which shouldn't be done. I would add that there's a paper on uninformed.org assessing Kaspersky antivirus, and they mention several instances where kernel data and functionality is exposed to user mode, to unprivileged code, and shouldn't really be. Static and dynamic analysis. I'm a reverse engineer myself, as you saw at the start. I'm not here to tell you how to do that. There are plenty of courses, talks, and books on the subject if you're interested in it. I find it beneficial because you know you're going to get code coverage. You can find all the entry points into the kernel code and then manually audit them, check if there are any particular issues. I mentioned signness. Subtle bugs are easy to find. Signness issues are blatantly obvious in a disassembly under x86 or x64 because the instructions are actually different. Memory overwrites are really trivial to find because memory access is pretty obvious. It might be a more subtle bug if someone's setting a particular entry in data structure, then that may be less obvious that that's controllable from user mode if you're doing a source code audit, whereas in a binary, you can just follow it through. If there's a large amount of kernel code, then obviously it's going to take a huge amount of time, and reverse engineering can allow you to focus in on the particular areas that you're interested in. So if it does kernel mode hooking, then you can say, okay, it's hooking these APIs, I can then fuzz these APIs. So it can help speed time, help you speed things up by finding areas to focus on for more dynamic analysis. As you're not actually running code, you're never going to cause the code to fall over, so there's no need to analyze crash dump, which can be awkward, particularly with some of the more arcane issues that are associated with kernel mode security, such as race conditions. However, the lack of symbolic information may be difficult. If you only have a binary with no symbols, then you've got no additional information. Source code can be greatly helpful in that case because you've got at least some idea what the person who wrote it is trying to do, though there are also the typical issues associated with source code review. Naming a variable often gives the intention of what that variable is supposed to be used for, but that doesn't mean that is how it is used. A programmer could bring in assumptions he's making that then are invalid or can be broken. And if he follows those assumptions, then you won't find those bugs. Source code analysis. Access to source is not common. If you're doing an internal audit for your own company doing a device driver or product that requires a device driver, then obviously you're going to have it. If you're a researcher or doing a black box test, then obviously you're not going to. With a suitable IDE, it will greatly help you speed up the process. As I said, assumptions by the coder may make things difficult. The source code auditing tools available and the verification tools from Microsoft help. And as I say, you can always do the typical code review tricks of searching for things like assume or hope or break. So once we've found our bug in the kernel, what can we do with it? Targets we're interested in are static or object function pointers. Static pointers will be pointers to kernel mode callbacks that may be initialized. The object function pointers in the object directory in the kernel. The kernel is, in a sense, object-orientated. Objects have an object header, associated data, and associated function pointers in a similar way to C++ objects. If you find the object in the object directory, then you can overwrite the function pointers and then point that to your encode in user mode or wherever and call that, and it'll be running as the operating system. Kernel variables, I mentioned at the start, the kernel needs to make a distinction internally between user mode and kernel mode memory, and it does that in Windows by one single variable, user probe address. So when dealing with buffers from user mode that are verified internally by the kernel, so if you're using buffered I/O in the kernel, then those pointers will be validated against user probe address. Typical protected mode descriptor tables, the LDT, GDT, and IDT. The IDT is an interesting one because the several interrupts are accessible from user mode, particularly int4 and int5, the divide by interrupt and overflow, and the bounds condition, bounds error, especially since they're unlikely to be triggered in usual operating system access. If you have a null point, if you can overwrite to a null value to an arbitrary address, then you can overwrite to the IDT the offset for int4, for example, trigger an interrupt, and then it will continue execution at 0 in virtual memory, which is in the user mode address space and can be allocated